Welcome everyone. And today we are very happy to have Yuhan Liu, who will talk about the recent work on Lindbladians for matrix product density operators.
Thank you. And it's very nice to come back to Chicago because I did my PhD here. Yeah, and afterwards I moved on to become a postdoc in Planck Institute. Yeah, so it is very nice to come back and then have the chance to share my research with you guys. Okay, so doesn't work now. Yeah. Okay. Sorry for the technical problem. Yeah. Can you all see the word or is it small? Yeah, because for some technical reason I cannot make it full screen. Yeah, so first let me thank my collaborators. We have postdocs at MPDO and UCM and also our PIs, Professor Nastasia and Planck. So I first like to mention a takeaway message, which is that we have a universal construction for the MPDOs, which are the RG fixed points. And furthermore, the parent Lindbladian very constructive satisfies some really nice properties, which is saying that they are frustration free and they have the minimal steady state degeneracy. And finally, we do a comparison between the parent Lindbladian and the parent Hamiltonian, and then we see that they have some different structure compared to the parent Hamiltonian. But maybe besides that, I also want to mention yet another takeaway message is that tensor network is actually an analytical tool. And see whether now this works. Yeah. Okay. So I guess that in North America, that most people tend to view the tensor networks to be a numerical method that allows you to do the simulation. So that is why I also want to emphasize this message that it is actually an analytical tool. Okay, so let me start from the very beginning that how to describe a quantum state. So in general, suppose we think about a general state of n spin, then in principle, we will need to specify all the superposition coefficients in a certain basis if we want to specify this state. So that is saying that suppose the local Hilbert space dimension equals to D, then we need to specify D to the power n parameters in order to specify this state. But however, suppose we focus on a special case, which is a ground state of local Hamiltonian, then in this case, we can do much better by using an ansatz called the matrix product state. So that is just saying that we can express all the superposition coefficient in a simple form, which is the product for all the matrices here. So here I take this product and then I take the trace, and then I use this to specify my superposition coefficient. So now each tensor has 3 labels. So we can say that it is a rank 3 tensor, and the physical dimension equals to small d. And here the horizontal legs are what we call the virtual bound, and the virtual bound dimension, we say it is capital D. So you can see that now the number of parameters equals to big D squared times small d, then times n. So it scales linear with your system size. So that is just saying that by using the ansatz for the matrix product state, we can reduce the number of parameters that we need to use for specify a quantum state. Okay, that is very nice. Now that I want to come to something that people probably less familiar with, something called MPS canonical form. So the basic idea is that there is actually redundancy in the MPS representation, which is saying that, so here I have this tensor A, which can generate a state that I can call psi A. But I can also have a different tensor B generate a different state called psi B. So it is possible that A and B as tensors are different, but they can generate the same quantum state. So psi A and psi B can be the same. So that is why I call the redundancy. So by using this redundancy, one can always bring an MPS tensor into something called a canonical form that represent the same state. And basically, the canonical form, we can view it to be a block diagonal matrix, and each block satisfies some nice property called normal. So basically, the canonical form is saying that by using the redundancy in the tensor, we can always bring a tensor into a block diagonal form, such that each block satisfies a nice property called normal. Okay, what do I mean by normal? It is a little bit technical and not needed for the later part, but therefore complete and showing here. So before I define what is this property called normal, I want to define injective, which is very simple. It is saying that suppose I build this tensor to be a linear map from these two virtual bound to the physical bound. So in this way, I can view my rank 3 tensor to be a linear map. And suppose it is injective as a linear map, then I can call this an injective tensor. So it is just a formal definition. And then what I can define normal is that if after blocking, so blocking means that I can combine several tensors together into a larger tensor. So suppose a tensor is injective after blocking, then I call it normal. Yeah. So so the technical part is probably not important, but just that normal is a nice property. Yes.
Just to check, is normal equivalent to unique largest eigenvalue of the transfer matrix? Or
Yeah, exactly. So I can right. So here I have a definition 1 for normal, which is from blocking to injective. So this is the first definition. And then, as you mentioned, there can be a second definition that can be from the transfer matrix. So so you can use the transfer matrix T. And in this case, you can say that normal if T has a unique unique leading eigenvalue. And what's more, the left and right leading eigenvectors are full rank. Leading eigenvector full rank. Yeah, so you can also define normal if the transform matrix satisfies both of these two properties, and then you can prove that these two definitions are equivalent. But then, so why do I use the first definition? Because blocking to be injective is quite powerful, because injective is saying that it's just saying that AI can span your full matrix algebra. Yeah, and then starting from this, you can borrow some results from the matrix algebra, and then use that to prove a lot of nice property. Yeah, so that is why I prefer to define normal from injective, but in principle, you can prove that these two definitions are equivalent.
Thank you.
Yeah, it's a nice question. Okay, so right, now that we want to ask a reverse question, suppose I give you an MPS with a tensor, can we find a geometrically local Hamiltonian such that it is a ground state? Okay, so you may think that it is very simple because I can just construct my Hamiltonian to be a projector. So by construction, it will be a ground state. However, the problem is to make it local, which is saying that I want to have a Hamiltonian to be a summation for a bunch of terms that only add on some neighboring sides. And back in 2006, there's a paper that showed the solution with the construction that they call the parent Hamiltonian, which can satisfy all the properties you want, that it is local and it is frustration-free, and it also has the minimal ground state degeneracy. Okay, so there is a formal construction, which I'm not going to talk about the details, not important for the talk, but the interesting points are the properties coming from this construction. So here I list 3 properties. The first is called the frustration-free, which is saying that the ground state for the full Hamiltonian is also the ground state of each local term. So by construction, the parent Hamiltonian has this nice property. And the second is that the ground state degeneracy equals to the BNT elements. Okay, so I guess I didn't talk about this enough. So when I say that it can be decomposed into blocks, it is possible that a same block can appear several times. So we really want to count the number for the independent block. And so that is what I call the basis of normal tensor. So basically the number of basis is the number of independent blocks. And why it is important is because the ground state degeneracy equals to the number of independent blocks in my MPS canonical form. And one can prove that it is also minimal, which is saying that it is impossible to come up with a local construction that has a smaller ground state degeneracy. So it is very nice. And finally, it is a artifice point if this state is a ground state of a commuting parent Hamiltonian. Okay, what do I mean by artifice point? Let me take a digression to define RG in the context of MPS. So it cannot borrow the ideas of coarse graining in the real space RG that people talk about in condensed matter. So the idea is that we first do a blocking and then we remove some redundancy by using isometry. So blocking is simple. You just combine several tensors together. And after that, so you can imagine, suppose you have a really big L, then here the output space dimension is d to the power L, so it will be super big. But actually, most of the degrees of freedom here are redundant in the sense that you can perform an SVD. So you will this horizontal to be your input and the verticals to be your output. So in principle, you can do an SVD in this way. And by doing the SVD, we can single out this isometry on top, because this isometry, roughly speaking, it is just doing a basis rotation from a smaller space to a larger space. So you can see that there is a lot of redundancy here. So we can define a new tensor by simply throwing away this isometry. And then we use this to define the tensor after one step of RG. So here I show the case where this L equals to 2. Then I can summarize this process in this way, that the quantum state after RG is blocking and with an isometry. Yeah, so there is a well-defined way to perform the RG in the context for the MPS. And with that, I can define the RG fixed point. So a tensor is called an RG fixed point if the tensor before and after this isometry is the same tensor. So from this RG process, the definition for the fixed point is very intuitive. It is saying that the tensor won't change after first RG steps. Yeah.
So do you understand correctly that under this notion of RG, entanglement does not change?
The entanglement between which and which?
Between the different blocks, the entanglement spectrum is unchanged after this?
Yes, you can say that. Yeah. Because so suppose I draw a better picture, if I'm going to draw that. So you can kind of think that before that, say I do this 3 to 1. Yeah, so I can take these 3 sides to be my unit, and then I perform some isometry here, something like this. Yeah, but then suppose you want to ask that what is the entanglement between, say, if you make your entanglement here, then it is not going to change. Yeah. Okay, I hope it is clear. Right. Okay, so now that I asked the question about the parent Hamiltonian, and then I shows you that there is a construction that comes with a lot of nice properties, but you can challenge me by saying that it is nice, but why do I care? Okay, so now I answer the question that why should we care about the parent Hamiltonian? Because it is actually quite useful. So suppose I talk to the experimental audience, then I'll talk about this adiabatic state preparation. But now that I talk to theory people, so I don't want to go to the details. But for the theory, the useful part is that we can use the parent Hamiltonian for the quantum phase classification. So so here I give a definition for the quantum phase for the pure state, that 2 systems are in the same phase if they can be connected by a continuous path of gap local Hamiltonian. So maybe some people are more familiar with the other definition that use the low depth local unitaries, but I can prove that these 2 definitions are equivalent. So we can just take this one that using the Hamiltonian. So the basic idea is that you can use the parent Hamiltonian to build a path so that you have a rigorous way to justify the phase equivalence. Okay, what do I mean by that? Okay, so here I first show the results that in 1D, suppose we don't impose any symmetry. All the possible phases are classified by the ground state degeneracy of the parent Hamiltonian, which, if you remember, equals to the number of independent blocks in your decomposition. And one can prove that the classification amounts to the classification for the artifice points. Okay, so maybe I can do a better explain later because I didn't make that figure very carefully. So that is saying that suppose I have a state which is general, not fixed point, then I can find the fixed point in the process that I described. So you can say that here I have a path from a state psi generated by this tensor, which is arbitrary, to its corresponding fixed point, which I call a fixed point. So you can do this for any state. So you can always bring a state to the corresponding fixed points. And then by using the parent Hamiltonian, you can construct this path along this RP process, and you can prove that it is gap. So that by using the parent Hamiltonian, you have a rigorous proof that the state is in the same phase as its fixed point. It is quite intuitive, but using the parent Hamiltonian, it is rigorous. So this is the first step that you show that it's in the same phase as your fixed points. And the second step is to classify the fixed points. And you can also do that by using the parent Hamiltonian. So the claim is that, so for the simple case, that you only have a single block in your canonical form. So let me take the simple case that you only have a single block. So suppose you have a first fixed point and the second fixed point, that they both have a single block, but with a different dimension. So here the dimension is dA, and here the dimension is dB. So by using the parent Hamiltonian, you can do a path between the Hamiltonian, the parent Hamiltonian for these two. So you can build a path of parent Hamiltonian connecting these two. And then you can show that it is gap. So with that, you can justify that suppose it has the same number of independent blocks that belong to the same phase. And then finally, you can use a different method to justify that suppose you want to jump between the blocks, then you will need to close a gap. So that finishes a proof for 1D that the phases are classified by the ground state degeneracy of your parent Hamiltonian.
Two quick questions. So when you gave the properties of the parent Hamiltonian a slide or two ago, the gap was not one of them, right? Or I'm saying it's also.
So I didn't show it here, but you can prove the gap rigorously. Yeah, but it is a harder proof. Yeah,
okay,
it can be proven.
Okay, great. And then second question. So you're saying that in the absence of symmetries, right? So there's just a classification in terms of the number of blocks. But is there some condition on the states that it can apply? Like, for example, if I have the W state.
Yeah, exactly.
And the GHZ state.
Right. So
what can you say about
that is a good point. Yeah, thanks for asking. So here I didn't mention a assumption that I'm interested in this uniform, which is saying that here all the yeah, okay. So it is quite natural because when you talk about the phase, you need to take the thermodynamics limit, and you probably want to have the translational symmetry. Yeah, so it makes sense to care about this uniform MPS. And then the case you ask the GHZ states, GHZ equals to G equals to 2. So you have 2 blocks, which is also kind of intuitive because it is, yeah. So one block generate 0, the product 0, and the other generate the product of 1. So then by using the results for the effect classification, you can see that it is in a different phase from the product state. And then the W state is more non-trivial because it corresponds to the case where G goes to infinity in the thermodynamics limit. So maybe some people are familiar with this result, that it is impossible to use a finite dimension uniform MPS to represent the W state, that the bound dimension needs to grow with the sequence size, so that we can, roughly speaking, say that it belongs to this G equals to infinity class. Yeah, so it is quite non-trivial. But recently, in our group, we have a work to say, because suppose you allow a boundary condition. So if you say I have all the states to be uniform, but then I can have an arbitrary boundary condition X. Yeah, so you can also define your state to be in this class that can carry a boundary condition. So suppose you can have a boundary condition, then the W state can be represented by a bound dimension equals to MPS. So we have a so in our group we have a written paper that classify this class, but the results will be more complicated.
Okay.
Yeah. Thanks.
Sorry, just to understand, so this classification applies to what you call uniform MPSs, which means stronger condition than translational symmetry, that the actual tensors are translationally symmetric. Okay,
Yeah.
thank you.
So like the W, there is the translational invariance, but not uniform. Yeah. So
Uniform means it's the same tensor.
same. Yeah, uniform means the same. Thanks for the questions. Right. So it is very nice that we have and then furthermore, in this paper, they also show the results when you impose the symmetry, and in that case, it will be classified that also by the group cohomology. Yeah. So that is the SPT story. Okay. So now hopefully that I have convinced you that MPS is interesting, and then we can use that to answer a lot of questions about the pure states. Now I want to shift the focus to the mixed states. So I guess people here are probably familiar with the Lindbladian, which is the master equation when we talk about the open quantum system under some certain assumptions. So now that we want to ask the questions, the previous questions, but in the context for the mixed states. So now we go back to the beginning and then ask, how do we describe a mixed quantum state? You may guess that we can do something very natural, that we just add one more leg. So I mentioned that MPS tensors are rank 3. So you may guess that we can just make it rank 4. And with that, probably we can have a way to capture the matrix product density operator. But however, there is a subtlety pointing out in this paper about the positive semi-definite. So like for the MPS, here the tensors can be anything, and they can always generate a valid quantum state. So there is no subtlety when we use the MPS representation. But however, if you want to talk about a mixed state, then you can imagine here the tensors cannot be anything, because otherwise it cannot be positive semi-definite. So it is more subtle when you want to study the mixed state. Moreover, in this paper, they prove that given this tensor M, asking the question that whether these families of MPDO are positive semi-definite in the thermodynamics limit is actually an MPR problem. So it is even impossible to tell in general that whether it is valid in the thermodynamics limit. So that looks very bad, but nevertheless, so I will convince you later that for a certain class of the MPDO, we can say 100% sure that they are valid. Yeah, but I will show that later. But before that, I want to ask a similar question for the MPDO. So we know that the MPS can be constructed as ground state of local Hamiltonian. Now that I want to ask whether MPDO can also be constructed as the steady state of local Lindbladian, so that motivates our projects to construct the parent Lindbladian. Okay, so as I promised, I will show you that there are many cases for the 1D mixed state can be captured by the MPDO. The first one is the 1D deep state of quasi-local Hamiltonian. So you take this H to be a quasi-local Hamiltonian, and then you construct a thermal state. And then this can be decomposed into 1D MPDO. And the second case, which is probably more interesting to the audience here, is that it can be the boundary of the 2D topological order. So for example, you can take the paths for the 2D torical and then look at the boundary, and the boundary will be a 1D MPDO that takes this very small form. So this is probably the simplest example. Moreover, recently, people talk about this so-called normalus density matrix and 1D, and this also has a very simple MPDO representation. Yeah, so it captures a lot of interesting states. Okay, so coming back to the Lindbladian, we want to construct a local Lindbladian, which is the summation for a bunch of terms. And then, so here is the definition for the steady state, which is the state that when you active becomes 0, or saying that after the long time evolution, it will go through this state. Yeah, so we want to construct this for the MPDOs such that the MPDO is in the space of this steady state. And then we call that parent Lindbladian. Okay, so let me first show you the summary of the results. So we give a recipe for the parent Lindbladian, and they satisfy the properties which we want. They are local, they are fluctuation-free, and more importantly, they reach the minimal steady state degeneracy. So we prove that there can not be other construction which is local and has fewer steady state degeneracy. And then we also do a comparison between the parent Hamiltonian, and then we also see some difference. So the first three properties are basically the same, but then there are some difference so basically for the parent Hamiltonian, the ground state degeneracy classify the phases, but that is not true for the parent Lindbladian, that there can be some MPDO whose parent Lindbladian has the same steady state degeneracy, but they belong to different phases. And then also they have different commuting property that the parent Lindbladian is not always commuting. Yeah, so just a quick summary. And then here is the key insights, which is probably not so difficult after you realize this point. So the insights come from RG. Previously, I flashed a construction of the parent Hamiltonian. So the insights comes from that we can return the parent Hamiltonian, but using this RG operator, V and V dagger. So here the V is the operator I use for this RG. So the intuition comes from that we can write the parent Hamiltonian in this way. So here we first use the V dagger to do a coarse graining, and then we use this V to do the fine graining. So the Hamiltonian can be constructed as a combination for the fine graining and the coarse graining process. And so then it is very natural to guess that suppose we can also define this algebra process for the MPDO, then we can do something very similar. So here, both T and S are quantum channels. And that is saying that when I use this T, I bring this one side MPDO to a two side. And then when I use this S, I bring a two side MPDO to one side. Yeah, so it is the quantum channels that I can use to change the MPDO during the RG. So suppose I can do this, then I can do something very similar, that I can find the fine graining quantum channel and the coarse graining quantum channel. And then with that, I built my local term in the Lindbladian to be this quantum channel minus identity. You can show that by this construction, it can automatically satisfy the Lindbladian structure. So it can be an Lindbladian that only has the jump operators, the Hamiltonian part equal to 0. Yeah, so hopefully I convince you that it is a very intuitive construction. This is nice, but the question, yeah, there are many questions. So first, I mentioned that for the MPS, we have a well-defined way to do the RG, but how about for the MPDO? So actually, there's a paper by Contaro who showed that there can be a counterexample where the RG doesn't exist. Yeah, so there can be a subtlety for how do you do the RG in the context for a mixed state for the density matrix. And suppose we can identify a class where we can construct this RG channels. The other points are whether this construction is actually useful in the sense that it is fluctuation free, and can we show that it has a minimal steady state degeneracy. So we answer all these above questions in the context for the RG fixed points. Because at the fixed points, we can construct the quantum channels and we can show the properties we want. Okay, so and there are some properties for the fixed points. Sorry, I didn't add this orders. Okay, so why the fixed point is so powerful? The reason comes from a fixed point structure theorem. So here I give a formal definition for the fixed points in the context for the MPDO. So very similar. Suppose there are two quantum channels that can bring this same MPDO tensor back and forth. Then I define this to be a RG fixed point. And by only starting from this definition for the fixed point, I can prove the following structure theorem, which is saying that I know how the fixed point looks like. So here I have two technical terms called simple and non-simple, which I don't want to define. It is a little bit technical, but there are a property called simple. And in this 2017 paper, which I think is a very nice paper that deserves more attention. So the authors have proven that suppose you impose the fixed point condition and another technical condition called simple, then the MPDO can have this decomposition. Hopefully that this kind of reminds you of something familiar. So the idea is that from the fixed point, you can, and with this simple condition, you can derive the conditional mutual information equal to 0. And then when the conditional mutual information equals to zero, you have a composition for the local Hilbert space. So I think there's a theorem proven by Andrea Winters and the other people that when CMI equals to zero, then it will lead to the local Hilbert space will be decomposed into a structure like this. So it will be decomposed into a direct sum of a error product. So basically, this structure comes from here and some other calculation. Then you can prove that what it is look like in this case. And you can also show that this actually corresponds to the if state of commuting Hamiltonian. So when you first impose the simple condition, it is the if state of commuting Hamiltonian. And suppose you want to lose the simple condition and think about the more general case, which are non-simple, then you can prove that the class of these MPDO bitcoins are generated from system of algebra, and which is saying that this case corresponds to the boundary of the 2D topological order. Yeah, is there a question?
I'm still trying to digest this formula, the bottom one, this simple RFP.
Mhm.
Why is that formula not always true? Like if that's so K ranges over some index, right?
Yeah.
If that is large enough, I could have imagined any object has this form. Like, can you give me some intuition for why this constrains the properties?
Right. So I think here this LK and RK also need to satisfy some other properties. Yeah. So here so this is a theorem with the complete form in this paper, but in the slide I only take the more intuitive part from the theorem. Yeah, so you are right. So suppose here the LK and RK can be arbitrary, then I can probably use that to generate a lot of states. But then if you check this paper, the RK and LK also needs to satisfy some other property, or there are some other constraints on this LK and RK. Yeah, so yeah, it can be a little bit more constraints. And then with that, you can show that it corresponds to the 1D thermal state of the commuting Hamiltonian.
So it is this assumption related to the transfer matrix of the MPDO?
Okay, so then maybe I can explain what I mean by simple. It is also related to the canonical form. So you can see that the canonical form really tells you a lot of information. So remember that for the MPS, we do this decomposition into the block, something like this. And then we call, say, each of them A, I, A. So here, A is the label for the different blocks. So for the MPDO, in principle, we can also do something similar, but we need to specify what is the direction. So I take this to be my I and J. Suppose I specify what is I and J, I can also take this to be a matrix. So I can also decompose my Mij into a canonical form and then label my different block by A. Yeah, like this. So here the simple means that so formally I have this block MK with this index. This corresponds to a block. So simple is saying that this is not zero for any A. Yeah, so roughly speaking, that after you so taking the partial trace won't reduce the number of block. Yeah, so that's the intuition for this simple, and suppose it is non-simple, after you take the partial trace, the number of block is going to change. Yeah, and then that will change some property.
So let me confirm. So here the partial trace is taken over the physical index.
Yeah, exactly. Yeah, so like suppose you have this row to be generated by a lot of these tensors. And then we'll take a say, and then you take a partial trace, so you trace over one of them. Yeah. Right, and then the second case is more interesting. There's a recipe that allows you to given the data from a six-star Wyckoff algebra. There's a recipe that allows you to generate an MPDO, which are the fixed points, and they are the correspond to these non-simple hybrid fixed points. Okay, so in the interest of time, I'm going to skip the formulas for the constructions, but mention some interesting results. The first case is what I mentioned before, the when the symbol states for the commuting Hamiltonian, and then it corresponds to the simple fixed points. So for this case, so if you follow the recipe for the parent Lindbladian construction, you can show some interesting property. So in this case, the Lindbladian is going to be commuting. And then with that, you can prove that the Lindbladian satisfies a nice property called rapid mixing. And furthermore, you can prove that it has a unique semi-state. People care about, okay, so I haven't defined the rapid mixing. So basically so there are several scales for the mixing time concerning a Lindbladian. So it can be rapid mixing. It can be fast mixing, or it can be slow, which is just a general case besides the other two. Anything else? So rapid means the mixing time scales as the polylog with your system size, and fast means the mixing time scales only to your system size, and then slow is just anything beyond. Yeah. In the mathematical community, I guess there are some people talk about the spectral gap for the Lindbladian, but the problem is that the finite spectral gap in the thermodynamics limit can only lead to fast mixing. Yeah, but the rapid mixing is a little bit stronger because it requires a faster mixing time. Yeah, so say that when you prove the phases of matter in the context for the mixed states, you want to have the rapid mixing.
Is this gap the gap of the Hamiltonian that defines the Gibbs state, or is it the gap of the Lindbladian?
Sorry. Yeah, so it's a gap for the Lindbladian. Yeah, so I think sometimes people will define the gap for the Lindbladian to be like, okay, so you are guaranteed to have a eigenvalue here, but there can be something else like this. So the gap is defined to be this difference. Yeah, so I think the intuition people think is that it captures the decay rate, but there are some subtlety in the proof that it can only lead to the fast mixing, but not the rapid mixing. Yeah, I think it is a very common misunderstanding, so I kind of want to highlight this a little bit. Yeah, so rapid mixing is a nice property for the Lindbladian, and then for this class, you can prove that the parent Lindbladian will be rapid mixing. And actually for this class back in 70s, there is a construction called the Davis generator. So here we have an independent construction from Davis, and it actually scales a little bit faster because the Lindbladian will be commuting. So in this sense, we do a little bit better job compared to Davis. Right, okay, the second case is the case for the boundary for the 2D topological order. And then in this case, you can see a separation. So generally, we can have a 6-star Wyckoff algebra, but suppose we also impose another property as a constraint, then it becomes the 6-star Hopf algebra. So 6-star Hopf algebra has one more property compared to the Wyckoff. And then we can show a separation for the phases, because for this class, we can prove that it has a commuting rapid mixing Lindbladian that has the minimal steady state degeneracy equals to the number of blocks. So there is a separation that when it satisfies this property, then it becomes then the parent Lindbladian become rapid mixing. So this includes the case of the torical boundary. So the torical boundary has a rapid mixing parent Lindbladian, which is probably not very surprising because you can also use a finite depth quantum channel to construct it. So it is just consistent.
Oh, sorry. So for example, for a peak state of a generic local Hamiltonian, is the corresponding MPDO simple or not?
So I think in that case it would be simple, but not fixed point.
I see. And also here for the rapid mixing is proven using the property of commuting, but not frustration free.
Actually, commuting. So you can use commuting to prove frustration free. So commuting is a really so for the Lindbladian, commuting is a very strong property that you can prove a lot of things. So in general, non-commuting Lindbladian can be rapid mixing, but suppose it is commuting, the proof is super simple. Okay, and the third interesting point is about the commuting. So for the parent Hamiltonian, for the fifth point, it is always commuting. But this is not always true for the parent Lindbladian, because for some class, you can prove a novel theorem that it is impossible. And the intuition comes from the Lieb-Robinson bound, because suppose you have a commuting Lindbladian, then it is rapid mixing, which is saying and then combined with the Lieb-Robinson bound. So okay, I should say in this way, for the class of the MPDO that has the long range correlation, suppose it is commuting, then you can generate this long range correlation fast enough that violates this Lieb-Robinson. So so that's the intuition to prove this novel theorem. So like in this very simple case, which is the mixture for 0 and 1, but it has the long range correlation. So so we cannot build a commuting Lindbladian for this case. And finally, as I mentioned earlier, in the context for the Lindbladian, the phases of matter is not classified by the steady state degeneracy, because you can just write some very simple company example that you can take a torical boundary, follow the recipe to write down the parent Lindbladian, and then the steady state degeneracy equals to 2. And you can also take our state with the long range correlation, follow the recipe, and then you can show that in this case, the steady state degeneracy also equals to 2. So so just by constructing a very simple example, you can see that the phases of matter is not classified by steady state degeneracy.
What was your definition of phase equivalence in this context?
Sorry. Okay, so it is a good question. Yeah, so here I mentioned this rapid mixing because you can use that to define a version for the phases of matter, which is saying that if you have rho 1 and rho 2, suppose you can find a Lindbladian, local Lindbladian such that it brings rho 1 to rho 2 in this time scale polyglot, then you can use that to define a partial order between rho 1 and rho 2. And suppose you can also find another Lindbladian that comes back within this time scale, then you can say that these two are equivalent.
One more question, you probably explained it, but I didn't catch it. How do you define this time t? Like you said, it's not a gap.
Yeah,
How is
sorry. Yeah, so I didn't define that, and it is defined in this way that you do a Lindbladian for any initial state, rho initial, minus your steady state, or suppose you have a space of the steady state, then it will be a projector to the space of the steady state. So here you have this difference, and then you take this one node, and you call this to be an error. So there is a formal definition, but I'm going to show the more intuitive one. So the intuitive one is that this error goes to 0 when t in the thermodynamics limit when t is greater than polyglot factor. Yeah. Is this clear?
See, so you fix, I see you take, it's like a different order of limits maybe than one might think of. So you say you scale both t and n. T scales like a polylog of n, and then you say in that.
Yeah, so here it will be a function per system size. Yeah. And then you say that when say okay, so when in this time scale and n goes to infinity, okay, and t, then this error as a function of n, it will go to 0.
That should be true uniformly for all initial states, or oh no, the initial state, like the one you've drawn on the left picture there. I see.
Yeah, so
for a particular initial state.
So this is the definition for the rapid mixing Lindbladian. Yeah, so suppose you call a Lindbladian to be rapid mixing, then it would require for all the initial states. So you can see that it is a really strong statement.
But here, your statement that you have rapid mixing Lindbladians.
Yeah. So this is a little bit different. So here the statement is that if you use this to go from one and another, and then you define this to be of error and t, and then similarly, suppose you have these conditions that error goes to 0 under this condition, then you define it to be a partial order between rho 1 and rho 2. Yeah, I think it's rho 1 greater than rho 2. Yeah, so there is a subtle difference that for this case, you will need to require for all the initial state, but then for this case, you specify your rho 1 and rho 2. And just as a small comment, so here I show this phase equivalence definition using the Lindbladian, but I think in kinetic matter, people are probably more familiar with a second definition, which use the low depth quantum channel, low depth local channel. Yeah, maybe Proton. Is more familiar with this. Yeah. So as I mentioned before, for the pure state, we have two definitions, and then you can prove rigorously that they are equivalent. So similarly, for the mixed state, you also have these two different definitions. And then I think it is a common belief that these two should also be equivalent, but the proof that I know only works for one way, but not coming back. Yeah, so I guess it is still an open question to rigorously prove that these two are the same. Yeah, but just a comment for the face.
These two definitions don't seem analogous. It doesn't seem like quite a good analogy with the pure state case, because both definitions are kind of state-based definitions rather than parent Lindbladian or parent Hamiltonian definitions. It's both about getting from one state to another rather than finding some path among some parent object.
But then I think that in the case for the pure state, I guess you only talk about the connection between the two different states or the two different Hamiltonian. Yeah, so in this sense, I would say that they are quite similar. You were saying that for the case for the parent Hamiltonian, so you have this H0 and H1, and then you will need to build a path that
it would be more like saying you have a parent Hamiltonian that's parent Lindbladian that's rapidly mixing, and some continuous path of them that go from L1 to L2, where L1 is rapidly mixing to rho 1 and L2 is rapidly mixing to rho 2, I would think.
Right, okay. Then, yeah, so that in this sense, it is, yeah, so there's difference between the parent Hamiltonian context. Right.
So just to check, so on this slide, to come back now that you have both definitions, these two states are different with respect to either definition, is that correct?
Yes. Yeah, so I guess it is just a that we lack a formal proof.
So for example, the first definition maybe not proven, I guess. Like it's believed but unproven that starting from one you can't rapidly equilibrate to the other one. Like just look at your definition one there on the
right, because for this one, this state can be connected to the product state and the definition. Yeah, but this one cannot. Yeah, so rigorously you can specify that they are in the same phase. But what I was saying that hasn't been proven is the equivalence between the phase definition for the first and the second one. Yeah, so I think for all the cases that we know, they will give the same results. Yeah, but we don't have a formal proof that specify they really are the same. Yeah. Okay, so yeah, so I think I'm out of time, so I just quickly mention that something can be interesting. Yeah, so for me, so there are two interesting directions. The one, of course, is to go beyond this point, which can be quite challenging, given that the algebraic procedure is not known. And then the second interesting point, but also challenging, is going to the higher dimension. So remember that in the past, I showed a very powerful structural theorem, which is saying that in 1D, by only imposing the definition for algebra, we figure out that how all the fixed points should look like. It is quite powerful. Yeah, so I think it would be nice if we can also do something similar in 2D to that under the context for the tensor network, can we figure out the vector for all the fixed points? And yeah, so I think it will be a challenging but very important question. Yeah, so that is my last slide, and I thank you for your attention.
Any questions?
So
Yeah.
do all yeah, I think you mentioned this. So there are some renormalization fixed points that do not have a rapidly mixing one. That's right.
Yeah.
Okay, and these are the ones with long range correlations. That's the reason.
Right. Actually, so I think there are several cases. The one is a case that has a long range correlation. The second is a case is in this weak hop, no hop. So the proof appears in a later paper by my collaborator. Yeah, but in this case, he managed to prove a no-loss theorem for this case to have a alternating Lindbladian. And finally, there is a recent work. Okay, so so I think he proved in the context for the local quantum channel. Yeah, so but I guess that maybe a similar proof can work for Lindbladian. Yeah, and the other case is a case that I mentioned here. Yeah, like for this class that MPDO that carries some forms of the anomaly. And yeah, so there's a paper coming from parameter, and I think the speaker will come later on. Yeah, so they also proved a no-go theorem for this class of the state, which only has a short range correlation, but you cannot build a low depth quantum channel. Yeah, so there are several cases, and I think it would be very interesting to ask that whether we can build a framework or for all the cases where a no-go theoretic exists.
Any other questions? No further questions. Excellent.